Hi guys, this is Miss Colson, and today we are going to look at ionic bonding and how we name an ionic bond or write a formula. First, let's do a quick review. There are three types of bonds. Ionic bonds contain either a polyatomic ion or a metal and a nonmetal. Covalent bonds contain only nonmetals, and metallic bonds contain only metals. Covalent bonds share electrons, and ionic bonds transfer electrons. So let's dive into the ionic bonds a little bit more and how we name them. Ionic bonds form when electrons are transferred. The transferring of an electron forms either a cation or an anion. Cations are positively charged atoms that have lost electrons. The way I remember that is a cation. If you'll notice the T, which I've highlighted in green, also forms a positive charge symbol. So T and cation for positive charge. Remember, the ultimate goal is to have a full outer energy level. So let's look at lithium. Lithium in its neutral form has 3 protons and 3 electrons. The positively charged proton and the negatively charged electron cancel each other out to make it neutral. It is easier for lithium to lose 1 electron than it is for lithium to gain 7. Therefore, lithium loses 1 electron, and it now has 1 proton that is no longer being canceled out by an electron, giving lithium an overall +1 charge. Now, most atoms are trying to fulfill the octet rule where they have 8 electrons, but remember, the first energy level can hold 2 electrons. So by losing 1 electron, lithium is now happy, it is now stable. It has these 2 electrons, which it is stable because its first energy level has 2 electrons. Hydrogen has a +1 charge because it is in group 1A. Group 1A, every element in group 1A has 1 valence electron. It is easier to lose 1 electron than it is to gain 7. Magnesium is in group 2A. It is easier for magnesium to lose 2 electrons than it is to gain 6 electrons, therefore magnesium has a +2 charge. The same with calcium. Calcium is also in group 2A. Every element in group 2A has 2 valence electrons. It is easier to lose 2 electrons and become a +2 charge than it is to gain 6. Aluminum is in group 3A. It has 3 valence electrons and is easier to lose 3 electrons than gain 5. Therefore, overall, aluminum has a charge of +3. An anion is a negatively charged particle. It has gained electrons. The N in anion for negative charge. Anions have a negative charge. Again, the overall goal is to have a full outer energy level. So let's look at fluorine. Fluorine has an overall 9 protons and 9 electrons in its neutral form. It has 7 valence electrons. It is easier for fluorine to gain 1 electron than it is to lose 7. So, it gains 1 electron, therefore, it has an extra negative not being canceled out by a positively charged proton, giving fluorine an overall -1 charge. Chloride has a -1 charge because it too is in group 7A. It has got 7 valence electrons, and it is easier to gain 1 valence electron than it is to lose 7. Oxygen has a charge of -2 because it has 6 valence electrons. It is easier to gain 2 electrons fulfilling this octet rule of 8 than to lose 6. Phosphorus has a charge of -3. because it has 5 valence electrons. It is easier to gain 3 electrons, giving it a negative 3 charge, than it is to lose its 5. The same with nitrogen. Nitrogen also has a negative 3 charge as well. Notice that our anions are not named like they are from the periodic table. Our chlorine is now chloride. Oxygen is now oxide. So what we do for our anions is we drop the last syllable and we make it IDE. So phosphorus becomes phosphide. Nitrogen becomes nitride. So that's very important. Our anions, we're going to drop that last syllable and we're going to add IDE. Cations, on the other hand, are named the same as they are found direct from the periodic table. All right, so let's look at how we form an ionic compound. We have to look at the atoms or polyatomic ions. We have to assign their proper charges known as an oxidation number. We have to crisscross and then simplify. So let's look at calcium chloride. Calcium has a charge of +2. Chloride has a charge of -1. We now need to crisscross. So the charge becomes the number of the opposite ion. So calcium has a charge of +2. That number 2 becomes the number of chlorides. Chloride has a -1 charge, so that becomes the number of calciums. You are bringing the number only, not the charge, not the positive or the negative, just the number down diagonally. So the 2 for calcium becomes the two chlorines, and the 1 in the charge for chloride becomes the number of calciums. Now, when you only have 1, you do not need to include the 1, so we write it as CaCO2. By just having a Ca, it is understood that there is only 1 calcium. All right, let's look at number 2, magnesium oxide. Magnesium oxide, we have a magnesium with a charge of +2, and oxygen has an oxidation number or charge of -2. We are going to crisscross those charges. So the 2 for magnesium comes diagonally down and becomes the number of oxygens, 2. The 2 in the oxidation number or charge of oxygen becomes the number of magnesium atoms. So we have Mg2O2. Now, just as in math, when you can reduce, we always need to reduce or simplify in chemistry as well. So Mg2O2, we're going to divide by the biggest common denominator, in this case, 2. So magnesium has 2, so 2 divided by 2 is 1. And oxygen has 2, so 2 divided by 2 is 1, leaving us with MgO. Make sure you always simplify when you can. Ammonium oxide. Ammonium is a polyatomic ion, NH4 plus 1. Oxide is O minus 2. Again, we're going to crisscross. So the number of ammonia, for the oxidation number in ammonia 1, becomes the number of oxygens. The number in the oxidation number of oxygen 2 becomes the number of ammoniums. We just move those numbers down diagonally. Notice we have put ammonium into parentheses. NH4 2 O1. Whenever you have more than one polyatomic ion, you must always put in parentheses. Again, we don't need the 1 beside O because it's understood to be 1, so we just rewrite it as parentheses NH4 2O. Magnesium hydroxide. Magnesium has a +2 charge, and hydroxide is a polyatomic ion with a -1. The 2 in magnesium becomes the number of hydroxides. The 1 in hydroxide charge becomes the number of magnesiums. So we have MgOH2. And again, our OH is in parentheses because we have more than one polyatomic ion. When we write a name If it involves a transition metal, we must always include a Roman numeral. There are two exceptions to that rule. Silver always has a +1 oxidation number, and zinc always has a +2 oxidation number. These are two transition metals that do not ever get Roman numerals. So let's look at what we mean by Roman numerals. Transition metals are able to donate a varying number of electrons. Therefore, because their oxidation number is not always +1 or always +2 or always +3, we have to write in a Roman numeral what the oxidation or charge is of that transition metal, and we do so by using Roman numerals. So Cu+1. Cu is copper, and it has a charge of +1, so we put a 1 in Roman numerals. Cu+2, that has a charge of 2, so we write it out as copper 2. Now it is important to note, this is not the number of copper atoms. It is its charge or oxidation number. That is what's important. It is its charge, not the number of atoms in a formula. So let's do a couple. Fe+3, that is iron 3. It has a charge of 3, so we write that in parentheses. Cr+2 is chromium 2. It has a charge of 2, so we write that in parentheses. Sn+4, that is tin 4, and Pb+2 is lead 2. Now you may have noticed tin and lead are not transition metals on the periodic table. They fall into the p block elements on the periodic table, not the d block elements known as the transition metals. So why did we assign tin and lead Roman numerals if they are found not in the transition metal section? And the answer to that is because tin and lead are exceptions to the rule. Just as silver always has a charge of +1 and zinc is always +2, tin and lead always get Roman numerals. So these are the exceptions to our transition metal rule. Let's look at how we write out a name. CaO. This is going to be calcium oxide. Our cation always gets the name direct from the periodic table. Our anion always gets the last syllable dropped and is made into IDE. So Ca is calcium on the periodic table. O is oxygen. We drop that last syllable, make it "ide," so we get calcium oxide. K2S. That is potassium sulfide. Potassium straight from the periodic table. Sulfur, drop the last syllable, make it IDE, sulfide. CuO. Now copper here is a transition metal, so we have to include a Roman numeral. This is going to be copper 2 oxide. This has a charge of 2 because when we crisscross, O has a -2 charge, so we would get 2 coppers. All right, and we would end up with 2 oxides, so Cu2O2, which reduces down to CuO, copper 2 oxide. Fe2O3. All right, when we crisscross here, notice oxygen has a charge of 2, and we do have 2 ions. Where did the 3 from beside oxygen come from? That came from iron's charge. We crisscross our charges and move the numbers down. So what is the charge of iron? It is iron 3 oxide. Notice again, that 3 does not tell you how many irons we have. Look at the formula. The formula is Fe2O3. I have 2 atoms of iron in the formula. But iron has a charge of 3, so it is iron 3 oxide. Ionic bonds form if a cation, which is positive, and a negatively charged anion come together. Opposite charges attract and are going to hold the cation and the anions together. Remember, opposites attract, negatives repel. So in this example, lithium has a charge of +1 and chloride is a -1. So they're able to come together and bond because we have the opposite positive and negative charge. Lithium and sodium can never form a bond together because opposites attract, like, repel, and lithium and sodium are both positive, so they would push away. Ionic bonds form what we know as salts. Now, we are not talking about just the salt that you put on your food when you sit down at the kitchen table. Any ionic compound is a salt. So, every ionic compound in the examples that we have just practiced with are all salts, and that's very important. A salt is where an ion attracts its closest partner. So a positively charged lithium is going to attract the closest negatively charged anion of chloride that it can. These ions are going to be pulled together into a tight structure known as a crystal lattice, and it forms this 3D structure where the positive of the cation and the negative of the anion are attracting the opposite from all different directions. They are held together by bonds. Now, when energy is released, when 1 mole of a compound is formed from gaseous ions, we call that the lattice energy. Now, we're not going to talk too much about lattice energy in the purposes of our class. You will talk a lot more about it when you take AP chemistry. All right, but lattice energy is the energy formed from the or released, when 1 mole of an ion crystalline compound is formed. Now, the unit cell is also known as a formula unit, and that is the smallest repeating unit in a crystal lattice. We write a chemical formula for an ion, and we write it using its unit cell or its simplest ratio. So when we wrote Mg2O2, I told you that you had to reduce and simplify it down to MgO. The reason we simplified that as MgO is because ionic compounds always appear in nature in that unit cell or formula unit, the smallest ratio of cations to anions. All right, so in MgO we had one magnesium and 1 oxygen because we reduced it down. So just a quick review. When we name an ionic compound, ionic compounds contain either a metal and a nonmetal. They have to have either a metal and nonmetal, or they have a polyatomic ion. We do not generally use Roman numerals with our S and P block metals, except for tin and lead. We do not use prefixes like we do in covalent naming either. If a transition metal, that D block element, is found within a compound, then we use Roman numerals to specify its charge, with the exception of silver and zinc, because silver always has a +1 oxidation number and zinc is +2. And again, no prefixes as in our covalent compounds. When we name the cation, we use the name of the element direct from the periodic table. When we name anions, we drop the last syllable and we add IDE. Now, polyatomic ions, we use the name of the polyatomic ion regardless of whether it is a cation or an anion. We don't drop syllables and change to IDE if it is a polyatomic anion. We use the ion's name direct from the reference tables in which you were provided at the very beginning of the year on day 1.